Okay, we'll go ahead and get started. Just a couple of quick administrative notes. First of all, the course notes will always be posted, but starting next week, I'm going to ask you to print them out yourselves before class. So if that's okay, because I'm using my copier at work and I'm probably starting to push the limits on the amount of copies I can do for personal purposes. So as I said, the notes will always be posted the night before. So I'll ask you if it's not a big burden to print them out yourselves. And I'll try to have a couple of copies, in case for some reason you aren't able to print, but just from here on out, I ask the expectation will be is that you print out your own course notes. And also, the only other administrative item is no homework tonight, but I will be handing out your first homework next week. So just, you know, be ready for that. Yes, I know. And so with that, we'll go ahead and get started. Okay. So what we're going to do this week and then probably a little bit next week is we're going to do a review of some of the fundamentals of elasticity theory. This is going to be nowhere near as complete as you'd get if you took a continuum mechanics course, or just add a couple things here. Nowhere near as complete as if you took a continuum mechanics course or a continuum mechanics course or a theory of elasticity course, but cover just enough of the basics so that we'll all be using the same terminology and definitions, and also the base, since I know a lot of you have not had continuum mechanics yet. So this way, the basics so that cover everything that should be necessary for you to know in order to understand what the topics we're going to cover in this course. So the first thing we're going to start with is stress, which is a concept you were introduced to even far back as sophomore strength materials, but now we're going to do a more in-depth. So we start off, so we imagine a material point in space, and we have our three-dimensional Cartesian axis, xy, and z, and x, y, and z, and we define an infinitely small area. Now, obviously, as I'm drawing it, it's not infinitely small, but for the purposes of the theory, assume that this is an infinitely small area, based on the material point. And we say that a force, which will use the vector n to define the traction, acting, and this infinitely small area here has a normal vector n. And we can say that the and and we'll have the traction vector, but originally think of it as a force, and we'll define this traction vector as being equal to the limit of the force divided by the size of this differential area as the size of this differential area goes to 0. So our basic definition of a stress vector. And as we go along, we'll talk about how we get from the stress vector to the classic definition of stress that you're used to. So this area is defined as an arbitrarily oriented plane with a unit vector n. Now we have this vector, we have this vector here, and it can be decomposed into a component. Well, go on to the next slide. Come on. Oh, shit. Yeah, let's try this. This works. Okay. So, so the stress vector can be composed into a component, yeah, into a component normal to the plane, which is called the normal stress, and a component tangent to the plane, which is called the shear stress. So first we'll draw that here. So imagine here's our plane, and we have our normal vector. We have our normal vector n, which is normal to the plane, and we have our traction vector just acting at some arbitrary angle. So we can break this vector up into a component normal to the plane, which we call the normal, which will eventually be the normal stress, and a component perpendicular to the plane, which we'll call the shear stress. And with this normal vector, it's a unit vector. So we say that this normal vector can have, it's the components. It has a component along the x direction, a component along the y direction, a component along the z direction. So we say that it's equal to nxi plus nyj plus nz k, the components. And like all unit vectors, we can say that the sum of squares of the normal components are equal to 1. So what we can say is, and I hope we'll do it. So we can say the state of stress at a point we say that it can be completely defined when the components of stress are known on 3 mutually perpendicular planes. So we have our point, we have our x's in the x direction, and in the y direction, and in the z direction, and we have we have a plane perpendicular to the x direction with a component of our stress vector acting on this plane that's perpendicular to the x direction. We have our plane perpendicular to the y direction. We have our component of stress acting perpendicular to the y. And then we have the plane perpendicular to the z-axis, and we have our component of stress acting on this plane, which is perpendicular to the z-axis. And the stress vectors on each of the coordinate planes can be written in component form, because even though the plane is perpendicular to the axis, the vectors themselves are not perpendicular to the axis. So this vector acting on the plane perpendicular to the x-axis, it has components in the x direction, in the y direction, in the z direction. And the same for this t sub y acting on the plane perpendicular to the y-axis. And the same with this t sub z acting on the plane perpendicular to the x-axis. So we can write that formally, and we can say that this, oh, come on. So this component on the plane perpendicular to the x-axis has its x component with in the x direction plus the y component along the y direction and its z component perpendicular, z component in the z direction. And same way for the traction vector on the plane perpendicular to the y-axis, we can write it in a similar way with its x component and its y component and its z component. And then finally, for completeness, we have our stress vector on the plane perpendicular to the z-axis, and we say, and similarly, it's as its component in the x direction, plus its component in the y direction, plus its component in the z direction. So if you look here, we have three equations, and the way everything's set up, this looks like something that we can write in a matrix form. So what we're going to do is we're going to take this T subscript I superscript J, and we're going to use what we're used to as stress notation. We're going to call it sigma ij. So if we go ahead and do this formally, and we'll write it in matrix form. So we'll say that and T1, and we'll also use the one direction for one for the x direction, 2 for the y direction, 3 for the z direction. So we can say our three vectors are equal to our matrix sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, sigma 3, 3, all multiplied by our normal vectors n1, n2, and n3. So it's the same equation same expressions as was here, but we just took these three simultaneous equations, and these three equations, and we wrote them as matrix form. Now we're not going to do a whole lot here. Now we're not going to do a whole lot with this here, but there's also so the values of sigma ij, here in this matrix are the components of the stress tensor, which completely describes the state of stress at a material point. And you'll learn about this a lot more when you take continuum mechanics, but a tensor is a matrix, but the difference between a tensor and a matrix is this. A tensor represents physical quantities, so it's not just a random collection of numbers like you have with just a matrix like you learn in linear algebra class. And also, as I said, and again, we're not going to go into it in detail in this class, but a tensor also has to obey some specific rules, particularly when it comes to coordinate transformations, changing your frame of reference from your axes in one direction to your axes in another direction, and from one direction to another direction. And we'll be talking about that a little bit when we talk about principles, stresses, and next week we may go into just a little bit of specific detail about the idea of coordinate transformation. But what we can also do is we can also write this expression in some reduced forms. One form that's commonly used in continuum mechanics is what's called indicial notation, where we can say that the T sub I is equal to sigma ij times nj, and we can write it in a vector form as T is equal to sigma times n, and this is what's called indicial notation. And the idea of indicial notation is that repeated indices imply summation. So what we can do is, so for this, so if we have our T sub I is equal to sigma ij and j. So what we can do is, if it's non-repeated, I can be any value from 1 to 3. So we'll start off with T sub 1. So because J is repeated, it means we do a summation. So we say so I is 1, so we say it's equal to sigma 1, 1, n1 plus sigma 1, 2, n2 plus sigma 1, 3, n3. So J varies from 1 to 3, and we add each of these components together. Okay? And similarly, we can say that T sub 2, the component of our stress vector in the y direction, is equal to sigma 2, 1, n1 plus sigma 2, 2, n2 plus sigma 2, 3, n3. And finally, our stress vector on the plane perpendicular to the z-axis is equal to sigma 3, 1, n1 plus sigma 3, 2, n2 plus sigma 3, 3, n3. So we cycle I. This is I equals 1, I equals 2, I equals 3. And because J repeats, we sum A. J goes from 1 to 3, but we sum each of the components. So we first set J equals 1, then we set J equals 2, then we set J equals 3, and we sum these together. Then the same thing when I equals 2, J equals 1, J equals 2, J equals 3, I equals 3, J equals 1, J equals 2, J equals 3. So these are all ways to formally relate the stress tensor to the stress vector, which is effectively the force. So this is how we relate our forces to our stresses. Okay. And in this form, as we talked about, repeated indices imply summation. And the stress tensor, you can prove it with strain energy. You can prove that the stress tensor is a symmetric second order tensor. So what's important there is to realize from a mechanics point of view that sigma 1, 2 is equal to sigma 2, 1. Sigma 1, 3 is equal to sigma 3, 1, and sigma 2, 3 is equal to sigma 3, 2. So even though they're different components by the laws of mechanics, they have to be equal to each other. And give me one just second too. I thought I quieted my phone. There we go. And so if you know the normal vector and you know the stress tensor, you can compute the stress vector, which is related to the force. So if you know the stress vector and you know the stress tensor, you can compute the normal vector. If you know the normal vector and the stress tensor, you can compute the components of the stress vector. Now, Now, what we've been talking about here is the full three-dimensional definition. So this is where we allow things to take place in the one direction, and the two direction, and in the three direction. So we allow for the idea that forces and stresses can be acting in all three coordinate directions. Now, from a practical point of view, in engineering problems, a condition we run into a lot is the condition called plane stress. And plane stress is a state of stress where all of the stresses, normal stresses, and all of the shear stresses directed perpendicular to the plane are assumed to be zero. And by the way, in our definition, just to make sure, sigma 1, sigma 2, and sigma 3 are normal stresses, and sigma 1, sigma 1, and sigma 2, are shear stresses. Which makes sense because these are each of the cases. These represent the components of the stress vector perpendicular to a plane, which is acting in the direction perpendicular to the plane. But anyway, so as I was starting to say, plane stress is a state of stress in which the normal stresses and the shear stresses perpendicular to the plane are assumed to be equal to zero. And where this is appropriate is if you have a very thin structure, like the skin of an automobile or other applications, where if your in-plane dimensions are much greater than the through thickness direction. Now obviously we're not in a cartoon world. Everything has three dimensions in real life, but from a practical point of view, if your through thickness dimension is much smaller than your in plane dimensions, the through thickness stresses can be assumed to be many orders of magnitude less than your in plane stresses, and thus for practical purposes, they can be assumed to be equal to zero. Mm-hmm. So, and these are just a couple, and so the loads have to be all applied in plane, and this through thickness direction has to be much smaller than the in plane directions, and these are just a couple of kind of cartoony applications of where plane stress is a valid assumption. So as I was saying, the normal and shear stresses in the out of plane direction, the z direction out of the plane, are assumed to be zero because all the loading is in the xy plane and the dimension is assumed to be very small. Another way of looking at it is we can take in our structure, we can take an infinitesimally small element similar to what's shown here, and we can draw the stresses that are acting on this element. So this is just for the plane stress, and this element has a length dx in the x direction and a length dy in the y direction. And we have our normal stresses acting perpendicular to the planes of this element, the horizontal and vertical planes. And we have the shear stresses that are acting along the plane. So we have tau x, y, and usually when we think about shear, particularly in the plane stress case, x is the first subscript represents the plane that the face is perpendicular to, and y represents the direction in which the shear force acts. So tau xy as shown here means that it's acting on the face perpendicular to the x-axis, but it's acting on the y direction. And as we talked about, because the stress tensor is symmetric, tau xy does equal tau yx. and that's to preserve moment equilibrium. Because if they weren't equal, you'd have a moment, you'd have a rotation taking place, which obviously can't happen. Okay. And a lot of times for plane stress, we can represent the stress state in a column vector like is shown here. And just to note, even for the three-dimensional state of stress, you can also show you do it as a column vector. Obviously, it's a lot bigger. You have sigma x, sigma y, sigma z, sigma xy, sigma xz, sigma yz. And you'll see sometimes me along with other people will switch back and forth. Sometimes you'll see xyz as your subscripts. Sometimes you'll see 1, 2, 3 as your subscripts. X me, just always remember, X is equivalent to 1, Y is equivalent to 2, Z is equivalent to 3. So as I said, me and lots of other people will switch back and forth. So, any questions to this point? Okay. So now we're going to talk about the idea of principal stresses. And the idea of principal stresses, and I'll do a cartoon of this in a moment, which will hopefully help to explain it. We'll say, so the idea is looking at this two-dimension cases, we can take this cube here and we can rotate it in such a way so that when we rotate this cube over some angle in reference to this modified coordinate axis system, we'll call it x prime and y prime, all we have is normal stresses. We don't have shear stresses. Now, the idea is the load we apply, because one of the things I always remember, stress is an artificial construct. Stress is something we invented in mechanics in order to allow the equations we developed to make sense. In real life, the real types of things you apply to a structure, you apply forces to a structure, and structures move. They have a displacement. These concepts of stress and strain that we've referred to in mechanics are totally not arbitrary, but they're invented. They're conveniences we come up with. Stress is a convenience that was developed to describe how forces are applied to structure. Strains, as we'll talk about strains later, were developed as a way to define the displacement of a structure. So because of that, because we referred stresses and strains to a particular coordinate axis, when we rotate the coordinate axis, these specific values will change. Now, the thing to keep in mind, and this is always a concept that students have to think about for a while before they get these two states of stress, this state here and this state here, they're describing the same load that's applied. By changing our coordinate axes, we're not changing the load we're applying to the structure. All we're changing is the frame of reference that we're applying the load to. So we're just choosing to rotate our coordinate axes so we have a frame of reference such that in this frame of reference, all we have is normal stresses and no shear stresses. So the load is the same. We're changing the coordinate axes, which means the way we describe the stresses that refer to that load are referred to that load are different. And these normal stresses are called the principal stresses, and the angle that we have to rotate to reach this state is referred to as the principal direction. So we've rotated by some angle theta. And where these principal stresses are is that, particularly if you're comparing to strains, a lot of times in the principal stress state, if you're looking to see if a structure has failed or not, that the principal stresses, because you're just dealing with the normal stresses, that's a good way if you're looking to determine if a structure has yielded or failed at a particular point, because when you do your material characterization test, you're doing a unidirectional tensile test, so all you have is a normal load. You don't have a shear load. So by rotating, what you're doing is you're determining the stress state, which is kind of equivalent to the unidirectional tense. So principal stresses are something that a lot of times people like to deal with. So what we're saying is that from a cartoon sense is we're saying is we have some plane with a unit vector with a normal vector n, and we've defined the angle of this plane so that the stress vector is parallel to the normal vector and perpendicular to the plane. So we can say that our stress vector is just equal to some scalar lambda multiplied by the normal vector. Okay. And using, okay, give us plenty of room, good. So using the relationship between the stress vector and the stress tensor, we can develop an expression which will lead us to be able to find the principal stresses. So we know in our general definition that our stress vector is equal to the stress tensor multiplied by the normal vector, which, and also by the definition we just talked about for the case of principal stresses, it's also equal to this scalar lambda times the normal vector. And something we'll do just to make the math work better is we'll take this lambda and we'll multiply it by, and I'll define this in a second, the identity matrix multiplied by the normal vector. And what the identity matrix is it's just a convenience in linear algebra. It's basically how we define one in linear algebra. So this identity matrix just has one on the diagonals and zero in the off diagonal term. So it's basically taking something and multiplying it by one, but where using the identity matrix comes in handy is it allows us to, all the rules of linear algebra when you do matrix addition and matrix addition, your matrices have to be the same order. When you do matrix multiplication, the orders of the matrices have to even out the right way. So by using the identity matrix, it allows us to do that. So what we'll do is we'll take this equation here and this equation here, and we'll write it for simplicity in indicial notation, but then we'll break it out to regular matrix notation in a minute. So we can say that sigma ij nj, so sigma times n is equal to our scalar lambda times delta ij times nj. And delta ij is called the Kronecker delta, and this is, and what it allows us to do, it's a mathematical convenience. So for this delta ij, it's equal to 1 when I is equal to j. and delta ij is equal to 0 when I does not equal j. So this is just a way of writing the identity matrix using this indicial notation. So what we can do is we can take this term to the left side of the equation, and we can say that sigma ij nj minus lambda delta ij nj is equal to 0. And factor out the nj, we can have that sigma ij minus lambda delta ij multiplied by nj is equal to 0. So the trick is this is what we'll do to find the principal stresses, because the only way that this equation can be true for any and all cases, no matter what our stress state is, no matter what our stress state is that the determinant, and no matter how we've, how things are oriented, the determinant of sigma ij minus lambda delta ij has to be equal to 0. So that's the only, so this is what's needed to make this always true for any, for any condition of stress. And yeah, so what we can do then is now we can finally write things in matrix form, and we can say that the determinant of sigma 1 minus lambda, sigma 1 2, sigma 1 3, sigma 1 2, sigma 2 2 minus lambda, sigma 2 3, sigma 1 3, sigma 2 3, sigma 3 3 minus lambda. All of this has to be equal to 0. So it's a 3 by 3 matrix, which means the stress tensor is always real and it's symmetric. Therefore, for this, so with those conditions, the 3 roots of the determinant are real, have to be real numbers. So the determinant, when you go through all the math, and we're not going to do that, you end up with a cubic equation, and you get an equation for lambda cubed minus I1 lambda squared plus I2 times lambda minus I3 is equal to 0. And these i's, what they are, I1, and we'll write out what they are in a minute, but what's special about I1, I2, and I3 is they're what's called stress invariants. And what the invariant means is no matter how we change the orientation of our axes, even though, because we'll write it out for a minute. So for example, I1 is equal to sigma 1 plus sigma 2 plus sigma 3. So as we change our coordinate axes, the specific values of sigma 1, sigma 2, and sigma 3 will change, but the value of the invariant, the way that you add the 3 together, no matter how we change our coordinate axes, the values of these invariants will not change. So they are effectively the fundamental properties of a particular stress tensor. And likewise, I2 is equal to sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 1, sigma 3 minus sigma 1 squared plus sigma 1 3 squared plus sigma 2, 3 squared. And finally, I3 is equal to the determinant of the stress tensor, which is equal to sigma 1, 1, sigma 2, 2, sigma 3, 3, plus 2 times sigma 1, 2, sigma 2, 3, sigma 1, 3, minus sigma 1, 1, 1, sigma 2, 3 squared, plus sigma 2, 2, sigma 1, 3 squared, plus sigma 3, 3, sigma 1, 2 squared. So these are the value of the invariance. And like I said, no matter how you change your coordinate axes for a particular stress tensor, I1, I2, and I3 will remain constant. So what you do is you compute these values, you substitute it into this cubic equation here, and you solve for lambda. And so you solve the cubic equation, it gives the principal stresses, and these values can then be used to find the principal directions, the angle at which you have to rotate your axes to find the principal stress. Okay? And for like anything else, plane stress, both conceptually and numerically, it's a lot simpler. So for the case of plane stress, the principal stresses are defined as the maximum and minimum normal stresses in the two-dimensional plane. And these principal stresses act on a plane defined by this principal angle here, which defines the direction. So all we did is we took this, our basic XY plane, and rotate it. We have an X prime and a Y prime direction. And that's our rotated plane where we take our state of stress, which had normal and shear stresses, and now it only has normal stresses. So this principal angle defines the normal whose direction is perpendicular to the plane on which the maximum or minimum principal stress acts. And all right. So when you do all this, what you get, it's much simpler equation. So you have sigma 1, 1 is equal to, and when we, in writing it this way, when we say 1, 2, 3, we mean in the principal system, x, y, x and y, we mean in the original axis system. So sigma 1 is equal to sigma x plus sigma y divided by 2 plus the square root of sigma x minus sigma y, divided by 2 squared plus tau x y squared, and sigma 2 is equal to sigma x plus sigma y divided by 2 minus the square root of sigma x minus sigma y divided by 2 squared plus tau x y squared. So just to repeat this point one more time, the critical point to note is that the principal stresses of the element, it's the same state of stress as in the original coordinate system. So in the original coordinate system, we'd have normal stresses and we'd have shear, and we have shear stresses. So this state of stress and this state of stress are the same. All we're changing is the coordinate system that we're looking at it. It's the same way if you were in outer space and you flipped yourself upside down, the North Pole would still be the North Pole, the South Pole would still be at the South Pole. But since you flipped yourself upside down, now from your perspective, the South Pole would be at the top, the North Pole would be at the bottom, but the North Pole is still the North Pole. So the last thing we'll do with principal stresses is, given the following stress tensor, so we have sigma ij is equal to 57, 0, 24, 0, 50, 0, 24, 0, 43. And we are going to, and we want to find the principal stresses. So what's the equivalent matrix where these 24 terms go to 0, and what will the diagonal terms look like? So the solution is, first we find the stress invariance. So I1 is equal to the sum of the normal components, so 57 plus 50 plus 43, which is equal to 150. I2 is equal to 57 times 50 plus 50 times 43 plus 57 times 43. So we're going through the products of the various normal components, minus 0 plus 24 squared plus 0. So it's sigma 1, 2 squared plus sigma 1, 3 squared plus sigma 2, 3 squared. And we do that, we end up with 6,875. And I3 is then equal to the determinant. So it's 57 times 50 times 43 minus 0, bless you, 0 minus 0 plus 24 times 0 minus 50 times 24. And you go through and you do the math, that's equal to 93,750. So what you do based on this, you take these values and you plug them into your cubic equation, and you get that lambda cubed minus 150 lambda squared plus 6,875 lambda minus 93,750 is equal to 0. And then you use your favorite program for doing root finding, and you get lambda value. The roots of this equation are equal to 25 and 50 and 75. So those are our principal stresses. So what we can say is that our original stress tensor was equal to 57, 0, 24, 0, 50, 0, 24, 0, 43. And we found its equivalent principal form is 25, 0, 0, 0, 50, 0, 0, 0, 75. So these two states of stress are identical. They reflect the exact same load applied to the structure. The only thing we changed is the frame of reference to which we referred it. Okay. So we'll start one more topic before we take our break. So the one other thing I want to introduce a little bit, just because it's kind of, don't know how much we're going to use it in this class, but it is something that's interesting in terms of stress analysis, and we may use this topic a little bit when it, depending how deeply we get into applying plasticity to fracture mechanics. So there's another concept in stresses called the deviatoric stresses. And the way we define our deviatoric stresses is the components of the deviatoric stress are equal to the components of stress minus 1/3 times sigma kk times delta ij, our Kronecker delta. And this sigma mean, and we take 1/3, this 1/3 sigma kk, and this is, we refer to this as the mean stress. And by applying the rules of indicial notation, where if we repeat an index, we sum everything together, this is equal to 1/3 times sigma 11 plus sigma 22 plus sigma 33. And thus we can then write our deviatoric stress tensor as being equal to sigma 11 minus the mean stress, sigma 12, sigma 13, sigma 12, sigma 22 minus the mean stress, sigma 23, sigma 13, sigma 23, sigma 33 minus the mean stress. And what this does, breaking things up the way we do, what this does, and where this is important, it's useful in stress analysis in general. And we're not going to do it here, but when you use like the Tresca yield criteria and the von Mises yield criteria, it gets to a lot of these points. But what the idea is that these deviatoric stresses are the shear components of the stress tensor. So you see, if we look up here, sigma 12, sigma 33, sigma 23, though the values of those deviatoric stresses are the same as the original. So these are the deviatoric components. But for the normal components of the deviatoric stress tensor, we subtract out the mean stresses, because the mean stresses are volumetric stresses. It's like if you blow up a balloon. If you blow up a balloon, the stresses that are put on the balloon as you blow it up are volumetric stresses, because they serve to increase the volume. So increase the volume. So where in plasticity, where it's important is that plasticity is effectively a shearing process. So if you're looking to compute the plastic response of a material, all you want is the contributions of the shear portions of the stresses to the plasticity response. In classical plasticity as applied to metals, the volumetric stresses don't have any effect on plasticity. If you just have a pure expansion, you don't have any plastic strains. So, and talked about all this here. So the deviatoric stress invariance can be defined in a similar manner to the total stress invariance. So we have J1, which is equal to S11 plus S22 plus S33. And all the math is in the notes. I'm not going to repeat it all here, but the important point is that the first invariant of the deviatoric stress tensor is equal to 0, which makes sense because this first invariant reflects the volumetric response, and the deviatoric stresses are only are only the shear component. So it makes sense that J1 is equal to 0. And J2 is equal to 1/6 times sigma 1. Oh, uh, sigma 1 minus sigma 2 squared. And now this is plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared plus sigma 1 squared plus sigma 1 squared plus sigma 2 squared. And just a note that you can also do some math games to show that it's equal to I1 squared minus 3I2, or it's also equal to, if you look at the indicio notation, it's 1/2 times the matrix product of the DV toric stresses. And J2, if you look back from what your first undergraduate saw in mechanics class, and you compare the definition of von Mises stress, you'll see the definition of von Mises stress is awfully close to this here, because the von Mises stress is directly related to J2, because so J2, when you talk about yield, is a very important term. And then finally, that J3 is equal to the determinant of the DV toric stress tensor, which if you do all the math and you group things into invariance, is equal to 2 times I1 cubed minus 9 times I1 times I2 plus 27 times I3. So these are the definitions of the invariance of the deviatoric stress tensor. And like I said, J2 is one that's very important because it's directly related to the von Mises stress. So the last thing we will do before our break is just to finish this topic is examples. So for the following stress tensor, with our stress is equal to 5, 2, 0, 2, 2, 0, 0, 0, 8, we're going to compute the deviatoric stress invariant J2. So the first thing we have to do, we have to compute the deviate. So the first thing we have to do is we have to compute the deviatoric stress tensor. So the mean stress is equal to 1/3 of the sum of the components. So it's 5 plus 2 plus 8. So the 1/3 of the sum of the normal components. And then we have the deviatoric stress tensor. So we have 5 minus 5, which is 0. The shear components don't change. Then we have 2 minus 5, which is equal to -3, 0. And then 0, 0. Oh, and I did have a typo here. And then it's 8. In the notes, that last component should be 3. I'll write it correctly here. So 8 minus 5 is equal to 3. It's not equal to 5. Just something I never corrected from the last time I did this. But then I did have it right in the next step. So correct this in your notes. It was 5 in the notes. It should be 3. And then finally, we can use the definition of J2 to compute the invariance. So we have J2 is equal to 1/2 Sij. So we take each of the components in the dV toric stress tensor, multiply it by itself, and then, sum it all together and then divide it by 2. So this is equal to 1/2 of 0 squared, which is 0, plus 2 squared, plus 0 squared, plus 2 squared, plus plus -3 squared, plus 0 squared, plus 0 squared, plus 0 squared, plus 3 squared. And you do all this, you get 13. So that's our tour of everything related to stress. So any questions at this point? Okay. If not, it's definitely time for a break. So I have 6:18 on my clock, so we'll pick up again about 6:30. So have a good break. Okay, go ahead and get started. So, talked about stress. The next major topic is strain. So, the same way stress is related to force, strains can be related to displacements, which define the difference in position of a material point after deformations. And of course, we're always neglecting rigid body motion. So for the conditions of small strain, which is exclusively what we'll be dealing with in this course, where the displacements and the displacement gradients, the changes in displacements are small, we can define the strain in terms of the displacement vector u and the material point position x. So we can, in general, say that using our indicial notation that the components of the strain tensor are equal to 1/2 of the partial derivative of the ith component of u with respect to x sub j, where u is the displacement vector and x is the point position, plus the derivative of the jth component of u with respect to the x component of I. So a couple of specific examples. Epsilon 1 is equal to 1/2 of the derivative of u sub 1 with respect to x sub 1 plus the derivative of u sub 1 with respect to x sub 1. And we're going to, in just a little bit, relate this to the delta L over L type of thing that you're delta L over L type of thing that you're more you're more used to considering. Now, of course, this is sum of two things divided by 2, so it's just equal to del u sub 1 with respect to x sub 1. And then epsilon 2 is equal to 1/2 of the derivative of u sub 1 with respect to x sub 2 plus the derivative of u sub 2 with respect to x sub 1. Now you look in here, classic definition, and we're going to, in just a minute, talk about the relation between the classic definition and what you're used to thinking of when you think of strains. In the strict definition of mechanics, strain is a tensor, just like the stresses. And you can define principal strains and strain invariance the same way you did with stresses. And you can define mean strains and deviatoric strains the same way as you would with the stress tensor. So, as I said, in classic mechanics, strain is considered a tensor, and you go into detailed constitutive modeling, that type of thing. And we'll touch on it just the tiniest bit here, but if you get into detailed constitutive modeling, you'll deal with the tensor form of strain, not the engineering strain, what you're used to thinking about. Which, leading into that, when you study strength of materials as sophomores, and even in your basic undergraduate mechanics class, you're used to the idea of engineering strain. And engineering strain is more tightly linked to the idea of the deformation of a defined object. So we'll define engineering strain. We'll imagine a small cube is deformed, and first we'll look at the case where the cube is deformed in the x direction. So we have our, put our axes here, x-axis, y-axis, and we have our little cube here, and its corners are A and B and C, and we apply some force and we define it. So after deformation, we have still our x and y axis, but now we've applied some sort of force along the x direction, and we've stretched it out. Now, point A is at A prime, which is still at the corner, but we have B prime and we have C prime are the new locations of points A, B, and C after deformation, and this is, x prime and y prime. So we've deformed this cube, and so it started off here, it moved to here, and the locations of A, B, and C are now at A prime, B prime, and C prime. So this is now where we use our classic definition that we say the normal strain in the x direction is equal to the change in length divided by original length, the definition that you're familiar with. So we say that it's equal to the distance from A prime to B prime minus the distance from A to B, and divided it all by the original length, which is the distance from A to B. The classic, yes, question. Yeah, you're still using it. So it really is just x and it really is just x and y. It really is just x and y. So so now that so now what we can do is we can take this deformation and we can put it in terms of displacements and deformation gradients. So once again, we have our original cube with A, B, and C, and it has an original length of delta x, and then we deform it, and we have our new points A prime, B prime, and C prime, and we define the distance from A to A prime after we move it. We define that with our dimension u. That's the deformation. And then the distance from the far end, from point B to point B prime is equal to u plus the variation of u with x multiplied by dx. So to get from B to B prime, we move the amount u, but then we add in this extra term, which reflects the change in our deformation with respect to the x coordinates. So it's the u to get the same distance as it was to get from A to A prime to B, which would get you somewhat like here, and then you have to add in that extra bit to allow for the additional deformation. So the so we'll write it here. So the distance from A prime to B prime is now equal to delta x plus the distance, so delta x, the distance from A to B, plus adding in the terms from A prime to B prime, which is u plus derivative of u with respect to x times delta x. So this term here, but we have to subtract off the original u. So we can take now so given all this, we can take our definition of strain to find the strain in the x direction. So we know that the strain in the x direction is equal to A prime B prime minus A times B divided by the distance A times B. So epsilon xx is equal to u plus delta u delta x minus u plus delta x, all that minus delta x divided by the original length delta x. At delta x cancels with delta x. U cancels with u, and we divide by the delta x's, and we just get equal to delta u delta x, which is what we got from the definition of the tensorial strain in the tensorial strain in the one direction or the x direction, which makes sense. So for the normal directions, the tensorial strain and the engineering strain are the same. Okay. Now where things get tricky is, and similarly, the normal strains can also be defined as the ratio of the change in length in the x or y direction divided by the original length, which is the classic definition that you learned in, strength of materials. And we can go through a similar type of thing, and you can demonstrate that the engineering strain in the y direction is equal to the partial derivative of v with respect to y. Now, where things get a little trickier is where we start looking at shear. So we look at our differential element. Before deformation is this dotted cube. After deformation is the solid line. And you can see all these various displacements in the x and y direction which change, but also you notice these changes in angle here. So this change in angle and this change in angle. So this is alpha 1, we'll call this alpha 2. So we have this element before and after deformation. And what we define is the engineering shear strain is defined by taking this deformed cube and looking at the change in angle between the lines AB and AC. So AB and AC. So what we do is that the engineering shear strain is defined as the angle CAB minus the angle C prime, A prime, B prime, where the primes represent after deformation. So it's equal to alpha 1. So it's equal to alpha 1 plus alpha 2 because we take this little change in angle and add it to this little change in angle. It reflects the total amount that's equal to. So alpha 1 plus alpha 2 plus C prime A prime B prime equals the original CAB. So because this is small angles, we can say that it's approximately equal to the tangent of alpha 1 plus the tangent of alpha 2, because for small angles, the angle's equal to its tangent. So when we do all this, we can say that gamma xy is equal to v plus dv dx times delta x minus v divided by delta x plus u plus delta u delta y minus u divided by delta y. And where we get these, it's all related to is if you look at these various figures here. For example, the tangent of alpha 2, opposite divided by adjacent, is equal to V is equal to B plus delta V delta Y dy divided by the adjacent, which is this length, with this length here, which is V. So when we cancel out all our terms, we end up that it's equal to dv dx dx plus delta u delta y. Now, the important thing to note is that the tensorial strain is equal to 1/2 dv dx plus delta u delta y. So the engineering shear strain is equal to twice the tensorial shear strain. So the important thing is it won't matter so much for our class, but just the general note in constitutive theory. When you do constitutive theory, the engineering shear strain is not a tensor and it doesn't behave like a tensor. So when you look at doing constitutive equations and that type of thing, that fundamentally constitutive equations will always be done in tensorial strain. So you have to think about sometimes you'll have to convert from tensorial shear strain to engineering shear strain. So it's something just to keep in the back. So just something to keep in the back of your mind. Okay. And also for the plane stress case, we can represent the strains as a column vector. And then likewise for the three-dimensional case, we can also represent the strains as a column vector. So gamma xy, gamma xz, gamma yz. Okay. Now, one note, we're not going to, well, we'll probably do a little bit with this, but just to define the idea, similar that there's plane stress, there's also plane strain. And plane strain is defined to be a state where the strain, similar to plane stress, where the stress normal to the plane was equal to 0, in plane strain, that's defined to be a state where the strain normal to the xy plane is assumed to be 0. And where plane strain is appropriate is for the case of very long bodies with a constant cross-sectional area that are subject to the loading in the x or y direction and don't vary in the z direction. So like this idea here, you have a pipe, it's just subjected to vertical load. So the load is just in the xy plane. The load doesn't vary along the z direction. So you can assume that there's no deformation and assume this is a very long pipe. So the deformation is just in the x and y directions. There is no deformation in the z direction, thus there's no strain in the z direction. So plane stress means that it's very thin. There's no stresses in the out of plane direction. Plane strain is for a very long structure, where there's no strain in the out of plane direction. So that's a whirlwind introduction to strain. So the topic will start tonight and will finish next week is elastic constitutive equation. So elastic materials, which is what we'll start off with, and obviously linear elastic fracture mechanics, we'll start off with just assuming everything's elastic. So elastic materials, they're materials where the loaded material returns to its original configuration after unloading. So we pull on something, we let it go, it goes back to its original size. It goes back to its original size and shape. Now note that, for materials with plasticity, on the other hand, think of if you take a paper clip and bend it more than just a little bit, it changes its size and shape, and it has some permanent deformation. And what we'll be talking about in fracture mechanics, we'll start off with assuming everything's linear elastic, but then we'll build up slowly. The first thing we'll do is we'll say, okay, right around the crack tip, the stresses are high enough that we can have some plastic strains right around the crack tip. And then eventually we'll extend to the idea, okay, if the larger area of the structure is subject to plastic strains, then how do we account for that? So we'll start off with linear elastic, and then we'll build on from there, allow for some levels of nonlinearity and non-recoverable deformation. So for elastic material, the relationship between stresses and strains can be defined as a linear relationship. So using our formal tensor notation, we can say that sigma ij is equal to Cij KL times epsilon KL, or sigma is equal to C, which is called the stiffness matrix, multiplied by the strains. AndCijkl is a fourth order tensor which defines the stiffness matrix. And that's something which always confuses students. Why they use C to refer to the stiffness matrix, which stiffness starts with S, and then we'll talk just a little bit about the converse, is the inverse of the stiffness matrix, which we won't get to today, we'll get to next week, is called the compliance matrix, and that's referred to as S. And why they use C for the stiffness matrix and S for the compliance matrix is something that goes back into history, and yes, I know it doesn't make sense, but it's what it is. And the version of this that you're familiar with is just the unidirectional version of Hooke's law that you learned about, that the stress is equal to the modulus times the strain. Now, this is all written this way because officially the stress is a two-dimensional tensor and the strain is a two-dimensional tensor, which means that the stiffness matrix in the strictest definition of mechanics is a fourth order tensor, but we just don't deal with any things that way. And the nice thing the thing that allows us to do that is because, excuse me, the stress and strain tensors are symmetric, strain energy considerations can be used to show that the that the stiffness matrix is symmetric. So it can be proven, and way beyond the scope of this course, for example, we can say that C1212 is equal to C1221, and thus we can just refer to this as C12, and the thing that's nice is what it allows us to do is we can do everything in a nice two-dimensional form. So we take our stresses and we put it into a column form, sigma 1, 1, sigma 2, sigma 3, 3, sigma 2, 3, sigma 1, 3, sigma 1, 2. And one thing to note, and I'll probably flip back and forth. Different books, different references, the order of the shears can change. Some put 1, 2 first, then 1, 3, and 2, 3. Some texts put 2, 3 first, then 1, 3, then 1, 2. And what we can do is we'll refer to our stresses using a condensed notation where we have sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. And then we have a nice 6 by 6 matrix, which is C11, C12, C13, etc. and so forth, C16, and C21, C22, C23, etc. and so forth, C26, and all the way down, and we get C61, C62, C63, and we get C66, and multiplied by our string. So it's epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 5, epsilon 6. And so we write our strains in the column vector the same way that we write our stresses in the column vector. And remember, because our stiffness matrix is symmetric, C12 is equal to C21, C23 is equal to C32, and et cetera, and so forth. Okay. And this is all right now the standard tensor definition. When we go ahead, and this will be this will be next time when we put things in the engineering constants that you're familiar with, like Young's modulus, Poisson's ratio, shear modulus. Then we'll talk about the differences, between using engineering shear strains and tensorial shear strains, and what difference it makes in the shear terms in the stiffness matrix. And also, right now, this is a general form. So this is the general form. All it is for linear elastic. And we haven't made any of the simplifications we can do for what's called an isotropic material, which is we may dabble a tiny bit in composites depending on how the semester goes. I don't know if we'll get to it. But this is true for whether a material is an isotropic material, and an isotropic material means that the properties are the same in any direction, no matter how you pull on it, or a composite, which is an orthotropic material, means the properties are different if you pull on it in different material pull on it in different directions. So, but for most of what we're going to deal with in this course, we're going to deal with isotropic materials where the properties are the same in every direction. So for an isotropic material where the material behavior is the same in all directions, we're going to do a very rigorous looking at defining the equation to relate the strains and the stresses. And next time we'll get to how we convert this rigorous derivation to the equations using the constants like Young's modulus, shear modulus, Poisson's ratio that you're used to. So for the isotropic material, you can write the relationship between stresses and strains this way. You can say that the components of stress are equal to this constant lambda times epsilon 1 times epsilon 2 plus epsilon 2 times plus epsilon 3 times the Kronecker delta plus 2 times mu times epsilon ij. So this is basically the volumetric component, and this is the shear component. So this lambda and this mu are what are referred to as the Lemay constants. So they are the fundamental constants in in elastic constitutive equations. And as I said, next time we'll talk about how you relate the Lemay constants to the engineering constants that you're used to considering. So now, one thing we can do to look at what mu means is that's fairly easy, is that if we look at sigma 1, 2, that's equal to lambda times epsilon kk times delta 1, 2 plus 2 times mu times epsilon 1, 2. And also remember, all we're doing looking now is looking at tensorial strains, not engineering strains. Well, delta 1, 2 is equal to 0 because I doesn't equal j. So sigma 1, 2 is equal to 2 mu epsilon 1, 2. And this now here we can make the leap to the engineering shear strain. And we know that since 2 epsilon 1, 2 is equal to the engineering shear strain, it's equal to mu times gamma 1, 2. So we know mu is equal to sigma 1, 2 divided by gamma 1, gamma 1, 2. And as we learned in sophomore strength of materials, this is equal to the shear modulus G. So this Lemay constant mu has the same definition as the shear modulus that you were used to dealing with since the time you were sophomores. Now, the other thing to note is that an isotropic material has two independent constants. So in our case, the lambda in the rigorous definition, lambda and mu are two independent constants. And also, as you've learned about, this case is still, remember when we think in terms of the traditional engineering constants that you're used to thinking of, we have the Young's modulus, the Poisson's ratio, and the shear modulus, and we know that the shear modulus is related to the elastic modulus and the Poisson's ratio. And as I said, next week we'll talk about how we relate the engineering constants to the these Lemay constants, lambda and mu. Now, the other thing we can do is this equation here. We have the stresses in terms of the strains. We can also invert this equation and we can write these strains in terms of the stresses. So we take our original equation and we look at the specific case of I equals to j. So we have that sigma II is equal to lambda epsilon kk delta II plus 2 mu epsilon II. And we can say that epsilon kk, in this indicio notation, constants are independent. We can say that epsilon kk is equal to epsilon II. And for this delta II, the way we can define that is if you consider that the Kronecker delta is defined like the identity matrix that we talked about, that delta II is equal to delta 1, 1 plus delta 2, 2 plus delta 3, 3, which is equal to 1 plus 1 plus 1, which is equal to 3. So we can take this delta II and just replace it with 3. So, oh yeah, I did skip a step in writing down. So, oh yeah, so what we did, I did forget a step, is that in the original, so backtrack a little. So in the original thing, we do have that sigma ij is equal to lambda epsilon kk delta ij plus 2 mu epsilon ij. So epsilon ij is equal to 1 over 2 times mu sigma, nuts, sigma ij minus lambda epsilon kk delta ij. So this is what we do is, so what we're looking for is if we want to write the, so that's what led to what we're starting to do. So now we have that epsilon k. So now what we're looking to do is we need to put this epsilon kk in terms of some function of the stresses so that we have the strains in terms of the stresses. So that's what's leading to what we started here. So this is how we're starting this process. So we have the, so what we have here is we said I equals J, so we said sigma ij, sigma ii in terms of epsilon kk and epsilon ij. So we went through all this. So what we can do then is put a line here to say that this is now, back to the previous page. We can say that sigma ii is equal to lambda epsilon ii times 3 plus 2 times mu times epsilon ii. So sigma ii is equal to 3 lambda plus 2 times mu all times epsilon ii. And thus we can say that epsilon ii is equal to epsilon kk is equal to 1 over 3 lambda plus 2 times mu times sigma kk. So now we can take this and we can plug it into here, and ultimately what we get, what we get then is that epsilon ij is equal to 1 over 2 mu times sigma ij minus lambda epsilon kk delta ij. We plug in what we had before, and we have that epsilon ij is 1 over 2 times mu times sigma ij minus lambda over 3 lambda plus 2 mu times sigma kk delta ij. So this is our elastic constitutive equation with strains in terms of stresses, and this is in terms of the Lemay constants. So what we're going to do next time is we're going to go through and we're going to take these Lemay constants and we'll relate them to the engineering constants that you know and are familiar with. And then we'll do one or two other topics related to elasticity theory, and then we'll start our way through linear elastic fracture mechanics. So any questions on any of this stuff? Good. So not have a good evening. Try to stay cool, at least for the next couple of days. And see you next week. Thank you.